So hello everyone. So today we're going to be looking at the iodine clock reaction kinetics lab. So over here I have set up all our solutions. So just make sure that you have everything very well labeled because it is very easy to mix up these clear colorless solutions. Over here I have my potassium iodide, potassium chloride, the sodium thiosulfate plus the starch which is in there, which is going to be our indicator. And this side I have my ammonium peroxysulfate, and then over here I have my ammonium sulfate. And then I also have in the back a 10 milliliter graduated cylinder for each of these, and make sure that you don't mix up the solutions, otherwise they'll start reacting prematurely. So for the pre-lab video, I'm only going to do the first reaction for you just to show you what you should be looking for. I'll let you do the rest of the reactions because where's the fun in that if I do them all for you. For the first reaction, we need 10 milliliters of our potassium iodide solution, so I'll just go and measure that out into my 10 milliliter graduated cylinder. Okay, so there's my 10 milliliters there. Now, of course, this only goes up to 10, so I have over here my container where I'm going to be mixing everything together. So I'll just add this 10 right into there. And then for the next one, I'm going to go measure here my 5 milliliters of my starch solution with the sodium thiosulfate. Okay, so there's my 5 milliliters of that. Okay, make sure they're nice and well mixed. And finally I'm going to measure out the 10 milliliters of the persulfate, so the ammonium persulfate right here. Okay, so that's my 10 milliliters. Now, it is very important that you start your timing when the solutions are mixed. So this is where your lab partner comes in handy. When they say go, you go. So we'll start the timer, and then we'll just mix these things together. Okay. And then of course you want this to be well mixed, and you just keep an eye on it because the color change might be a little subtle. Okay, so hopefully you were able to see that. It's a little hard to see sometimes on camera here, but you should see kind of like a very dark bluish solution. So yeah, that's basically what you are looking for. And then you just go and obviously record whatever time that was. I wasn't keeping time because I can look on the video how long that was. But anyway, you will go and record those different times for the different solutions that you'll be making up, and then you can do your plotting from that. All right, and then for the next part, you will be looking at this at different temperatures. So very simply, you just go here, get a beaker filled with ice water or heated water, depending on if you're doing the hot one or the cold one, and then you will simply just go and obviously you'll get rid of this and stuff. And this stuff, by the way, can just go down the drain. It's just starch with a tiny bit of iodine in it. Just the one thing you want to make sure is between runs that this thing is dry, because we are dealing with concentrations being dependent upon how long the reaction takes. So if there is excess water in there, that obviously is going to dilute things, and your times are going to differ a little bit from that. So anyway, just make sure it's nice and dry there. And then you can go and very simply just measure out the amount that you need. That's just going to be our 10 milliliters there. Mix that together with our 5 milliliters of our solution. A little bit too much there, but it's all right. And then simply just go stick this in the solution here, just The one thing is when you do put in the water and stuff, just make sure that the levels aren't too high, because very easily you could get a Titanic situation where things tip over, and basically at that point you have to kind of start over. And then you go get our thiosulfate, or sorry, the peroxysulfate. And now this one you want to cool off as well, so very simply just take your graduated cylinder and just stick that in there in the water, because we want to make sure that everything is at the same temperature. So you just let that cool off for a minute or so, just to make sure everything is at equilibrium. Also have your thermometer in there. So also have your thermometer in here as well, so you know what the temperature is. And once you are happy that all these things are at the correct temperature, you can very easily just go and make sure, again, you read your temperature on your thermometer, and then you very easily can just go here and mix everything together. And you want to make sure you keep this cold or warm, because what's going to happen is, if you just leave it out in the environment, the temperature is going to change. So you want to make sure that that temperature is maintained. So anyway, basically just keep it there, and of course you will have watching the time on that.
Many tic-tacs later.
Okay, finally we have our color change. Okay, so obviously just be patient for this one. It will take a while to actually complete. So anyway, then you just do similar things for the hot water bath and the catalyst as well. Okay, I want to take just a few minutes to explain some of the mathematics behind the kinetics that we're going to be talking about here. So first of all, let's just have a very simple reaction. A is going to B. Now, for this reaction, we're going to be interested in the rate at which the concentration of A is changing into B. So the way we can express that is the change in concentration here, so delta concentration of A over time, so that's delta T, and we're going to be saying that this is going to be proportional to the concentration of A. So this is our little proportionality sign right here, and it's going to be proportional to the concentration of A raised to some power. And in this case, N is going to be equal to something like 0, 1, 2, etc. It doesn't necessarily have to be an integer value, but for the common ones that you're going to be seeing, at least at this stage, it's usually going to be an integer value. Also, because if we have a reaction here, and A is going to B, this necessarily means that the concentration of A has to be decreasing. So we're going to have a negative sign out in front. All right. So what this is saying is that the concentration of A is going to be changing over time, and the rate at which this changes is going to be proportional to the concentration of A simply just raised to some power. So it might be, if this is 0, then the concentration change is going to be independent of the concentration of A. If it's 1, it's going to be directly proportional. If it's 2, it's going to be proportional to that squared. Now, to get the rate equations, we're going to have to use a little bit of calculus. This is the only way that this is going to make sense. Now, the only way that we're going to be able to go from these rate equations or these rate laws up here to the integrated rate laws is by using a little bit of calculus. So we're going to dive into a little bit of calculus here, although I will define things so you hopefully are not going to be totally confused, and you can at least see where these equations basically come from. So calculus deals with infinitesimals. So here, this is a finite change in concentration over a finite time. Calculus deals with this finite thing going towards 0. So it's basically dealing with an infinitesimally small amount of time. And the way we write this would be d, concentration of A, dt. And since we're saying this is going to be proportional, we're just going to say that's equal to k, where k is simply the proportionality constant. times the concentration of A raised to the nth power. And again, don't forget our negative sign. So really what we've done here is replace these deltas by d, and d simply just means instead of being like a finite amount of time like 0.1 seconds, this is infinitesimally small amount of time. So it's like 0.00001 seconds we'd actually be dealing with in this case. Now, what does this actually mean, this dA dt? And by the way, you can't cancel out the d's. These simply just mean, like I said, a change in A over a change in time. Well, this right here is called our derivative. Okay. Now, what does this derivative actually mean? Well, let's start off with the common expression f of x, and let's just draw what our f of x actually is. So here, this is x on my x-axis, and over here, this is going to be my f of x on my y-axis, and I'm just going to have some arbitrary, curve up like this. Now, what we want to do is find out what the derivative at a particular point actually is. And what this is telling us is, let's say I were to go pick a point, let's say right over here. So I want to know at this particular point, how fast is this curve changing? Right? So as you could probably guess, if I picked a point over here, it would be changing quite rapidly. Over here, it's a little bit more slowly. Up here, again, it's a little bit more rapidly. So essentially what we're trying to do is figure out a line which is tangent to my curve at this particular point, and the slope of this line is going to be equal to the derivative of my function. Okay? So this line, of course, is y equals mx plus b, and in this case, the m is going to be equal to the derivative of the f of x. So df of x dx in that case. Now this is defined as the limit as delta x goes to 0 of my f of x plus delta x minus f of x all over delta x. All right. Now this, of course, would be my x value, and then this little point over here, so let's just say that point, that's going to be x plus delta x, and this right here is going to be my f of x, and that little point over here, that's going to be my f of x plus delta x. And what we're doing is we're taking the limit as this goes to 0, so in other words, my delta x gets smaller and smaller and smaller until, the 2 points are essentially right on top of one another here. So what is this basically saying? Well, if you remember back when we did our sugar lab and we were talking about finding the slope of a line, remember that was, the dy dx, the rise over run? Well, that's essentially what we're doing here. This is essentially looking at, the change in y, right? So this right here, that's essentially the change in the y, and then x minus x plus delta x, that's essentially our change in x, right? So this right here, this is going to be my delta x, this right here is my delta y, so this right here is just going to be the slope. So essentially what we're trying to do is figure out what is the slope of this line, which is again what we're trying to find out here. So that's the official definition. Now you look at a couple of examples here just so we can get an idea how this actually works in practice. So let's say I have a function here, in this case, is equal to k times x. So it's just a linear line in that case. So if I go here, d f of x dx is equal to my limit as delta x goes to 0 of k, and this is going to be, and now I'm basically, remember, f of x is equal to kx, so that means that's going to be k, and then this becomes x plus delta x, and then I go subtract off kx, and I divide that by delta x. So this, of course, becomes kx plus k delta x minus kx all over delta x. And as you can see right here, my kx's both cancel out, and then my k delta x over delta x means my delta x's cancel out, and this is equal to k. All right? Now, this should not be surprising, because if we look at this equation right here, this is essentially a straight line, right? So if I just were to plot this out, right? So this is my f of x, here's my x, and that's just, a straight line, kx. And what, of course, is the slope of a straight line? Right? The m, the slope of this, is going to be equal to k, which is what we found. All right. So that is, a pretty trivial, one to find the derivative of. We're essentially just finding what the slope of a straight line is, which, of course, is just the slope of the straight line. What is the slope of a constant? Okay. Here's a even trivialer one. So now, in this case, I essentially just have, a flat line in that case. So what is the derivative of that? Well, we can very easily just say, my df, of x dx, that's the limit. My delta x goes to 0. And now if I evaluate this at x plus delta x, that's just k. And I evaluate this at just, x, that's obviously also k. And I divide that by delta x. Well, k minus k is obviously 0, so that's going to be 0. And if we just, plot this out again, that straight line, right, this is just going to be, has a slope equal to 0, because, of course, that has no slope. So that's, again, not too surprising. And for my next polynomial here, we're going to look at our f of x is equal to kx squared. Okay, so that, of course, is a parabola. So if I go figure this out, so this is going to be my limit. Well, the x goes to 0 again. And this is going to be k, x plus delta x squared minus kx squared all over delta x. So, of course, this is going to be k times x squared plus 2 x delta x plus delta x squared minus kx squared all over delta x. And of course, I got that just using the FOIL method and everything. So if we look at this, right here I have kx squared. Here's a negative kx squared, so this is going to just go away. And then I have over here 2x delta x plus x squared, of course everything multiplied by k. Well, the delta x is going to cancel out with this one here. That's going to go away. And it's going to leave, cancel out with one of these. So that means that's going to go away. So this is going to leave me with 2kx plus delta x. And of course delta x is going to 0, so this is going to give me 2kx in that case. All right, so that is what our derivative of a parabola, of course, actually is. And that kind of makes sense because, if I start over here at 0, I have a slope of 0, and then as I keep increasing along the parabola, it becomes steeper and steeper and steeper, and this, it just happens, in regard to the 2kx. So if I start over here, it's not going to be quite as steep as if I started over there. Now, I'm not going to do every single polynomial here, but there is a general expression which is going to be very useful in a little bit here, is that for any polynomial, so just x to the generic n, this is going to be equal to n times x to the n minus 1. So we can kind of see this just by using this up here. So I have my kx squared. By the way, if you have any constants in there, they just come along for the ride. But you can see here n equals 2 in this case. So therefore, I should go and bring this 2 out in front, which I did. And then the 2 becomes 2 minus 1, which is just 1. So that becomes 2x. And then the k just kind of comes along for the ride. So this is going to be very important in a bit. Okay, and there's one final integral that we need to talk about because as we examine this, we'll notice that we have these, the natural log popping up. So we have to talk about where that natural log actually comes from because otherwise it's a big part we're missing. We're going to look here at the d, the natural log of x dx. So the derivative of the natural log of x with respect to x. So using our same old definition, we're going to have here the natural log of x plus delta x minus the natural log of x and divide that by delta x. So once I have this here, we're going to use the properties of logarithms. So if I add or subtract logarithms, that's essentially the same as multiplying or dividing those two factors inside of the logarithms here. So I can rewrite this as the limit delta x goes to 0. I'm just going to bring out the 1 over delta x on the outside here. And then I'm going to have here the natural log of x plus delta x, oops, and then divide that by x. Okay, so that is equivalent to this expression up here. All I did was I moved the delta x out in front, and then everything in my numerator up here, I just combined this into one expression. That's perfectly allowed because of logarithms. The other thing is with logarithms, if I have a factor out in front here, that's the same as raising it up to the power on the power of everything that I'm taking the logarithm of. So I can again rewrite this as the natural log of my x plus delta x over x, all raised to the 1 over delta x power. And this I can simplify by dividing through by x in both cases. I'm just going to leave off the limit part here as the natural log of 1 plus delta x over x, all raised to the 1 over delta x power. So at this point we need to remind you of one of the definitions of the exponential function. So e to the x can be written as the limit as n goes to infinity of 1 plus 1 over n to the nth power. Right? That's one of those definitions of that. Now, equivalently, since if n is going to infinity, we can look at it this way, that as delta x goes to 0, this means that 1 over delta x is going to infinity. Equivalently, as n goes to infinity, this implies that 1 over n is also going towards 0. Okay, so that's just kind of expanding upon those things. Okay, so it should be a little obvious. So you should start seeing the similarities between both of these. Obviously, the ones are the same, but here I have 1 over n, and as n is going towards infinity, 1 over n is going to 0. Well, that's the same thing as saying as my delta x goes to 0 over here. And then on the top, I have my n going towards infinity, right? But that's the same thing as my 1 over delta x going to infinity. So really, these are similar expressions here. So what I can do is I can go and substitute this basically in here and say that, let's seal this off, that this is going to be equal to the limit as delta x goes to 0 of the natural log of e of 1 over x. Okay, and of course, if we have the natural log of e to the 1 over x, this is again just using the power of logarithms. This is equal to 1 over x. What this is telling us, and finally, this is again the other important expression we need, is that the derivative of the natural log of x with respect to x is equal to 1 over x. Okay, so this is that other important expression that we need here. So that's derivatives. What we want to do from this equation right here is figure out what is the expression of a. All right, and if we look at the paper, we'll see that this says integrated rate law. So what we're going to need to do is introduce you to what an integral is. And an integral is essentially just an antiderivative. If we have our derivative, we can undo that by taking the integral. And I'm going to skip over a little bit with the integrals here just to keep this relatively short-ish. But if I have an integral here of a derivative, and then you have over here dx, this is just the common notation. So this right here would be the derivative, and then we're just saying that we're going to be integrating with respect to x, this derivative function here. And so this is just going to be equal to f of x plus an arbitrary constant. And the reason that arbitrary constant is there is because if you remember from this part right here, if I take the derivative of a constant, it's equal to 0. So if you have an integral, you don't actually know, this part right here is 0, you don't actually know what the constant was. So there's always going to be that particular constant there. And the other thing is that if we have an integral here between limits a and b, so these are generally going to be your starting and your ending points of your integration. And again, we have the same thing up here, our derivative. This is going to be equal to the function evaluated at b minus the function evaluated at a. So this right here is essentially the integrals, and these are the antiderivatives of that. So there are a couple of important integrals that we will look at. So right here, if I have an integral of x to the n dx, this is equal to x to the n plus 1 all over n plus 1 plus an arbitrary constant. And we can see that if I look over here at this expression, and if I were to go and take a derivative of this, we should wind up back at my x to the n. And we can actually just show that really quickly. So if I go here, take the derivative of this, so that's going to be the derivative of my x to the n plus 1 all over n plus 1 with respect to x. Using my definition here, I'm going to go bring down that n plus 1 down here, right? So this is going to be n plus 1, so that the power that's raised to, I bring that out in front. And then this is going to be n minus 1 plus 1, so that's going to be, by the way, that's there, to the n plus 1 minus 1. So this plus 1 minus 1 obviously just cancel out. And then I divide that by the n plus 1, which is my constant. So as you can see right here, the n plus 1's both cancel out, and I'm left here with x to the n, which is what we started with. Okay, so that's basically just proving that this is in fact, if I take the derivative of this, I get my x to the n back. Okay. The other integral that we want to see is if I have some constant here with respect to dx, this is just going to be equal to k times x plus c. And really, that's the same thing. We basically are just assuming in this case n is equal to 0, and that would go 0 plus 1, so that's just 1 on the bottom, and then x to the 0 plus 1, that's x on the top. So really, these are equivalent expressions, but just expressing them so you can actually see that. And then the final integral that we're looking at here is 1 over x. And we can actually see that this 1 over x is not actually going to work in this function right up here. Because in this case, 1 over x, that would mean n is equal to minus 1. If n equals minus 1, this is going to be negative 1 plus 1. So in other words, we're going to be dividing by 0. That is super not allowed in mathematics. So that obviously is not going to work. But, of course, as we just saw a few minutes ago, that is simply just going to be the natural log of x. And again, plus some arbitrary constant. Okay, so these right here are the important integrals that we're going to be needing to solve these things. All right, so we know enough information now that we can essentially go here and use our rate laws and figure out what our rate equations actually are going to be. So let's start out with a zeroth order. So in this case, my minus d concentration of A dt is simply just equal to k. All right, so this is a zeroth order reaction. What this is telling us is that the rate of reaction is independent of the concentration. All right, so as an example, think of yourself going to the airport. There is, a couple of people at the airport, or there are a whole bunch of people at the airport. Security doesn't move any faster. They don't care how many people are there. They take their same old time all the time there. So in this kind of a case, it doesn't matter on the concentration of people at the airport. How do we solve this? And this is definitely not the correct mathematical terminology here, but it's the easiest way of thinking about it. Basically what we're going to do is we're going to have our dt over here, and we're going to move it over to this side, and then we can go and integrate. What we're going to do here is we're going to move this over. So we're going to have minus dA, and this is going to be equal to k dt. And now what we do is we integrate both sides between the starting point, and that starting point is going to have a concentration of 0, and our ending point is going to have some concentration A of t. And over here, since my starting concentration was A0, that's going to be at time 0, and my concentration at AT is going to be at time t. In this case, this first part is going to be, if we look over here, we're essentially just integrating the constant, right? So in this case, we don't have any constant here, right? We're just integrating this. So this is simply just going to be my concentration, A, right? And then using this part over here, we're going to be evaluating that between the final and the initial concentrations. The way we would express this would be the concentration A evaluated from here's the ending point, AT, and then my starting point, A0. I probably should put the T outside, but whatever. And this one over here is going to be the same thing. So this is just going to go to K times T, and this is evaluated from 0 to T. So if I go here and write this out, that's simply just going to be A of T minus A0 is equal to K times T, because this is T evaluated at T, minus K times 0, which is just going to be 0. So I can write this out as my final rate law as AT is equal to KT. Oops, I forgot my negative sign over here. So I'll just move this negative sign. Yeah, I can just move the negative sign right here. So I put a negative sign here. Yeah, so notice this negative sign, I just move that over to here. That's all I did. Okay, there's my negative sign. So that's going to be negative KT plus, so this is moving over to that side, plus A0. And right here, that's going to be what we have. AT equals negative KT plus A0. That's exactly what we just found. Okay, so that's the integrated rate law for the zeroth. Now for a first order, we're going to have pretty much the same expression. So the negative dA dt is equal to k, but in this case, instead of being that a to the 0th power, this is going to be a to the 1st power. So that's the difference there. So what we do now, same thing that we do over here, except we want to have this a on the same side as my dA. So we're going to have on this side minus 1 over a dA is equal to k dt. And again, I'm going to go here and integrate both sides, and this is going to be starting from a0 up to at, and that's going to again go from time 0 to time t. So what we're doing is we're starting at time 0, that has a concentration of whatever a0 is, and we're going to time t, which has a concentration of a sub t. So this one, remember, here's our 1 over x expression. That's going to give us our natural log. And this part over here, that's literally the same as that part on that side. So just to make this a little bit easier, I'm going to move the negative sign over to this side, so make that a plus. I just move my negative sign over to the right. So this is going to be the natural log of a evaluated from a t to a0. And this is equal to, again, same thing like over here, my negative kt from 0 to t. So this is very simply the natural, whoops, make sure I'm off the page here, the natural log of a t minus the natural log of a0 is equal to negative kt, and again, minus k times 0 is just 0 there. So I can very simply just go and move this over to the other side. So this is going to be the natural log of a sub t is equal to negative kt plus the natural log of a0. And as you can see for our second one, that is exactly the same thing that we just wrote down here. All right, and then for the final one, we're going to look at the second order. So again, we have here our negative dA dt is equal to k times the concentration, but this is now squared. So just like I did in the last one, I'm going to go here, bring all my a's to the left side. My dt, I'm going to move that over to the right side. And so I'm going to have over here 1 over a squared dA is equal to k dt. And I'm just going to bring my negative sign over here automatically. And then I'm going to, just like before, integrate both sides. So again, from concentration at time 0 to the concentration at time t. And that's going to be from time 0 to time t. So as we integrate this, you'll see right here, this is negative 2 in that case. So using this expression here, that's going to be negative 2. So that means this is going to be x to the negative 2 plus 1 all over negative 2 plus 1 in that case. So this is going to become minus 1 over the concentration of A, evaluating that from A0 to AT, and this is going to again be the same thing like we had before, negative kt from 0 to t. And by the way, if you didn't get how I went from here to here, basically what we have here is, the integral of x to the minus 2 dx. And again, just using this expression we have, in this case, n is equal to negative 2. So therefore, this is going to be x to the negative 2 plus 1 all over negative 2 plus 1. So this is going to be equal to negative 2 plus 1, of course, is just minus 1. So that's x to the minus 1 all over minus 1, which is equal to 1 over, or negative 1 over x. So that's where, that came from. What I can do is just evaluate this like before. So that's going to be negative 1 over concentration at time t. And now I'm minusing a minus, so that's going to be plus 1 over the concentration at time 0. And this is equal to negative kt, like we had before. And again, just moving everything over to the correct side and flipping the signs. So basically, I'm going to, if I multiply everything through by negative 1, that's going to be plus, minus, plus, make our lives a little easier here. So it's going to be 1 over a sub t is equal to k times t plus 1 over a 0. And again, that's what we have right over here. 1 over at is equal to kt plus 1 over a over 0. Okay, so that's where those integrated rate laws basically come from. Now, as for the reaction and the experiment that we're doing today, so we have a couple of reactions that are occurring. So first of all, we have the 2I minus plus the S2O8, 2 minus, is going to iodine plus 2 sulfates. And also we have the reaction where the iodine is reacting with the S2O3 to form the 2 iodides plus the S4O6. And then once we have the iodides in there, they react with the iodines. Actually, I should say once we have the iodines in there, they react with the iodides to make the I3 minus. And this right here is what is going to react with the starch. Okay. So once we get that starch, we get that dark color that we're actually looking for. So this is the main reaction. This is kind of a secondary reaction. And in this case, this one right here is your limiting reagent. So this is only going to be basically, a few percent of my S2O8. So that's why, this is, I think, 0.005 molar. Meanwhile, this is 0.1 or 0.2 molar. So this is a very small quantity. So what happens here is this reaction is occurring. It's forming the iodine. And then this iodine comes down here. This goes down here. And then immediately reacts with this to form the iodine. Now, the iodide is basically, the iodine is being consumed, so it's being consumed over here, so therefore it's not around to actually react with the iodide to make the I3 complex, which reacts with the starch. So basically, as soon as this forms, it's being consumed over here. Now, what's going to happen is, since this is a very small quantity, this is eventually going to get all used up. And once this all gets used up, this secondary reaction over here gets cut off, and then the iodine over here can get fed into this reaction. Okay, so that's when you see that color actually develop there. And we can look at this as the chart. So here is my concentration of the I2 that is forming there, and then this is as a function of time. So it's going to have some kind of curve like this, and basically this amount that's going to be used up is going to be down here. Okay, so this right here is essentially the cutoff for like how much S2O3 there actually is. So it's going to be whatever I2 is minus whatever S2O3 is. Once that's all used up, then I'm going to start forming iodine, and basically past this point, we're going to be seeing that blue-black complex actually forming with the starch. So all these integrated rate laws that we just spent all this time solving, those aren't actually useful for this particular reaction, so I don't want you thinking that's what you're going to be using here. Okay, so to use these integrated rate laws, these would work great if we were able to plot the concentration as a function of time. Unfortunately, we can't do that with this particular experiment and the materials that we actually have. So instead what we're going to be doing is essentially looking at how fast this reaction starts. Okay? So in that kind of a case, what we're doing is, as you can see, when the reaction first starts, it looks fairly linear-ish, right? So if I were to go and then just draw, a straight line for this, you can kind of see it's linear in this regime. Now, if I were to have like a higher S2O3 concentration, it might be up here. It starts, curving. It's not quite as linear. But down in this regime, it's fairly linear. So we can assume that the delta part over here is essentially going to be identical, at least enough for our purposes, to the derivative. Okay, so as you can see, this is fairly linear. So again, remember we talked about slopes and derivatives and everything. Well, we're basically saying that over this small regime, the deltas here is going to be close enough to the derivative, which is going to give us our slope. And from that slope, of course, we can get an idea of the concentration. And remember, our rate laws here is basically some proportionality constant times the concentration raised to the nth power. So we're basically saying that my rate is going to be dependent upon the concentration. And as I go and change my concentration, either I'm going to double or quadruple it, you're going to say, well, if this is just k to the k by itself, as I change the concentration, the rate is not going to change. Here, if it's k times a, so it's going to be a first order reaction. If I double this, my rate is going to double. If I triple this, my rate's going to triple. If this is equal to 2, well, that's very simply just going to tell me that as my rate doubles, as my concentration doubles here, my rate is going to increase by 4 times. As it triples, it's going to increase by 9 times. Okay, so that's essentially what we're looking at. Is essentially this equation right there. But if we were to actually be able to plot out the concentration as a function of time, we could go here and use these integrated rate laws to actually figure out how the concentration is actually changing with time, and then figure out your k and your natural logs and your concentration zeros and your concentration at times t using these integrated rate laws that way. Okay, and this is what we are seeing in these concentrations. So notice right here, as I have my potassium iodide right here, notice this is 10 and 5 and 2.5. So right here, this is obviously doubling and doubling. And then over here, as I have my S2O8, here this is all 10s, these are 5, that's 2.5. So basically what you're going to be doing is when you're figuring out your concentrations and your times and everything, you just want to look and say, well, between these and this one, well, this concentration is going to remain the same, but in this case, the concentration, is half as much. And this one over here, if you compare these two, well, these concentrations are half as much, but these concentrations are the same. And then if I go and compare this one, I can compare 1 and 4. In this case, the concentration of the Ki is the same, but now this concentration is half as much. Same thing here, these concentrations are the same. And then basically we can also compare between these two as well. So these are both 2 and 6 are the same, and then 2 and 6, these are half as much as well. So this way we have some checks where we can compare not just one set of reactions, but a couple of set of reactions, so you can verify your ideas in those kind of cases. Okay, so I think I went through enough of this. So anyway, I'll stop this here, and if you've got any questions, you know where to find me.